voids care about the nonlinearity of the dynamics?
Yes, yes, that's right. So one thing is, like I said, because even voids, we expect them to be relatively linear, but then when we're actually looking for them, we're using nonlinear objects to look for them, like the galaxies. So that is nonlinear in some sense.
So we did detect the neutrinos already, right? Because of Big Bang nucleosynthesis and the CMB, I mean, the number of degrees of freedom of the radiation required
Yes.
neutrinos.
Yes.
3 species. It's the mass of the neutrino that we don't know.
That's right.
But we know that they exist.
That's right.
And so my question is,
well, if you talk to particle physicists, they might argue you saw some light relic particles. You don't know if they're neutrinos because we only detect their gravitational interaction.
right, but we know that there are 3 species, which matches the standard model.
That's right.
So
That's right.
plus or minus.
Yeah.
But is there any hope that these constraints will get even better or not? The constraints used to infer the existence of neutrinos from the number of degrees of freedom. Could they probe the mass at some sense?
You mean an effect?
Yeah, because a 0.1 electron volt is roughly the temperature of the universe
Yeah.
per combination.
Yeah.
So it makes, I mean, the mass of the neutrino makes a contribution to the energy density.
Yes.
So there is no hope of detecting that.
Detect them actually their neutrinoness.
Detecting their contribution to the mass budget.
Well, that's what we're trying to do. Yes.
No, but I'm saying.
He's saying in the CMB itself.
Oh, your CMB itself. I don't think CMB itself can constrain. I think in order to constrain them, you have to use all probes like BAO and CMB and
So
lensing.
my question is, why is it? I mean, if they make the mass is comparable to the temperature at recombination, why can't we, with more precision, eventually get to that?
Because you also have degeneracy with other parameter.
Okay.
Because now you're looking at suppression of the CMB lensing. Now people looking at, but then you can also just say initial power spectrum is already low. So that's the degeneracy they can't break unless you add in lower redshift information to see how it transitions as a function of redshift. Yeah.
Let's start here. We have plenty of time. No, we'll start with someone.
Okay. So when you define the voids, right? Are those voids defined in 3 dimensions?
Yes.
So I think one thing that becomes very tricky with voids is that how different things start to look can be very sensitive to what you use as the tracer field. Right?
Yes, I do have.
So
Yes.
right. So for example, if you have, for example, a different theory of gravity, right? So you have basically perturbations to GR on large scales or something. You find that these void profiles can look, and the abundances look very different.
That's right.
But actually, different ways of defining voids can separate theories quite nicely. So you have some statistics that use 3D void fundamental, but some statistics that use like line of sight things.
Yes, this is exactly like I put in backup slides because this is somewhat depressing to show. In the void community, unlike halos, which is just a spherical, really simple thing, which people might disagree as well. What is a halo? Voids, yes. So here I'm showing you a void comparison project result. Here are the dark matter particles, and they just give out to different code writer and say, tell me what is a void. And then the green one is what they define as a void. Some of them it's just a sphere. They say, if you go over this order density, then you're a void. And some others defined by the walls of the void. So it can be any shape, so it's really hard to quantify. And some other is a square. I really have no idea what's happening here. So using different wayfinder, you have totally different answer. The thing is, as long as you stick with one, the physics is really clear. However, even within the community, they're still arguing which one is the best to use. Yeah. Therefore, the non-popular use of voids right now to constrain cosmology.
Yeah. So you said that neutrinos, so higher neutrino masses, the more suppression growth you have. But wouldn't you also get the same thing with different models of dark matter? So how can you just say if matter isn't completely cold, dark matter isn't completely cold?
That's right.
How would you expect to disentangle those things?
there's many things that can mimic neutrino signature, different model of dark energy, different model of dark matter, if they're interacting, or baryons, they just blow things out. It's also suppression. So the key is we hope those things, they behave consistently as a function of time. And the neutrino has very specific signature as a function of time, as a function of scale. So we want to combine different redshift information to break this degeneracy.
And then one quick follow-up. Then what is, because you don't include baryons in your models, right?
Yes.
So what is the energy density of baryons compared to what you would expect for the mass considered neutrinos?
Much higher. So
Baryons much higher?
energy density, baryon is 5%. Neutrino is much less than that.
So then, would you expect baryons, like if you included baryons, you would see more drastic differences in structural formations if the energy density is higher?
So that's part of the reason I come here. I want to learn about baryons. And I think from the past work people did, so if you remember the neutrino change in matter power spectrum, so here, the suppression starts already at 100 megaparsec. So, but baryons from all the simulations we see so far is around here. So suppression from baryons is like pretty small.
Oh.
And you don't expect to blow out baryon to like 100 times of your virial radius.
Neutrinos should suppress growth on larger scales than baryons.
Yeah, yeah. So we.
Except for the big statistics. The big statistics.
Yeah.
Because the peaks is really the peak.
Well, you can also use different smoothing scale of the peak the statistic and then combine them. And then another reason non-Gaussian statistic might be nice is, yes, they are both two-point function and non-Gaussian statistic. They are both sensitive to baryons, but they might be sensitive in a different way, that if you combine them, you can even constrain the baryon parameter, we hope. I don't know yet.
I have a question about this one. So you cut off like N1.
Yeah.
And yeah, I wonder what happens when you go further, like to the scale of 4 galaxies in the Milky Way. Do you like still expect this to be flat? And can you just from the masses of those galaxies?
So you can already see some hint when I do the nonlinear power spectrum. They do not continue to be flat. They actually have a little spoon shape, like tilt up. It is because when you are already entering the we call it one halo regime, where you're probing the center of a halo, and virialization and making them more similar. Neutrino doesn't matter as much there.
So do you plan to run simulations to like?
I think my simulation actually go much beyond this. Yeah, I can see that spoon shape more clearly. I didn't plot it out here. Yeah, I can go up to 30 megaparsec. No, 30K in K. Yeah, yeah.
Right. Yeah, I think calculating Milky Way is like 1,000 or so. So I guess there's some way to go with that.
Yeah. Also, data here, we don't really trust data anymore. Like just too messy.
Oh, but I mean, you have it locally, like in the Milky Way and the
Yeah.
local group.
Yeah.
I'm
Okay.
very good at it. Like,
Yeah.
some people would claim the best data.
Yeah.
Okay.
Sorry, this sounds like a pretty trivial question, but how does neutrino interact with other things in your simulation?
So neutrinos do not interact with other things in my simulation. They just interact gravitationally. Yeah. Because they're free stream.
Okay, I think with that we'll finish here. Let's thank Jia again. We will be around until Friday, all day of Friday. So if you want to meet with